team. So now we're looking at section 1.6, where we're looking at both average and instantaneous rates of change. So one thing to keep in mind are the units of your rate of change. Remember it's referring to the slope of a function. Okay, so if we're looking for that slope, we're looking at a change in y over x. So that means when we're interpreting any rate of change, average or instantaneous, we're going to have your output or your y value per one x input. So for example, if we're doing the units of rate of change and f of x represents the number of turtles, that's our output. So we're dealing with the change of f of x over the change in x, and f of x is turtles, and x is years, then the units of that rate of change is going to be number of turtles per year. Same thing for B. If we've got the number of miles and x represents hours, then the units here is the number of miles per hour. In C, if f of x represents the cost in US dollars and x represents the number of bikes produced, then the units is going to be dollars per bike. I mean, we've done slopes before where maybe we had, 3 turtles. Oops, can't spell turtles. In 2 years, we have a slope of 3 halves. You could say that there's going to be 3 turtles every 2 years, but if you were to actually divide that, that means 1.5 turtles per year. So generally, we don't separate so many turtles, so many years, so many y's over so many x's. We just divide it or consider it reduced, and it's going to be turtles per 1 year. Now let's focus on the difference between an average rate of change and an instantaneous rate of change. An average rate of change is when we're looking for a rate of change between 2 points. And we've done this before. Remember, the average rate of change uses what we call a secant line. So in this picture here, let's imagine a point P, and that occurs at the input value X. And we'll say a point Q up here somewhere that occurs at another value of X, all right? So we can say that this distance here between these 2 X values, let's say that's a distance of H. So we can refer to this second X value as X plus H. So if we're to find the slope of that secant line, that line between P and Q, we're taking an average. So the slope of a secant line, we can say is the function value at x plus h minus the function value at x. Again, this is representing the q, this is representing the p, that output value, divided by the difference in their x's. Well, notice if we take the x plus h minus the x, then that's just going to give us h in the denominator. So f of x plus h minus f of x. So this is the difference quotient. We've been doing it all along, right? But now we're just defining that space between x and the next x is just having a distance of h. So when you subtract that 2, the change between those 2 x values is just going to be h. So here's what we're doing for an instantaneous rate of change. We are looking for a rate at a single point, okay? Or just put in the number 1, at a single 1 point. And then I put, spoiler alert, this is actually the derivative. The derivative is the slope at a single point. Let's talk about what that means. Let's put back in our p-value at x and our q up here at x plus h. And remember this distance here we called h. Imagine if we took that q, suppose there's a line, there's our secant line between p and q, and we moved that q closer and closer and closer to p, Okay, so the secant line is getting smaller and smaller and smaller, which means this h is also getting smaller. The distance between x and your next x is approaching 0. In order for it to be instantaneous, it has to be just at that point. So we're getting really, really, really close to p in the very next point, even though theoretically there's no such thing as a very next point. So if we're looking at the slope of the tangent line, we're going to take the limit as that distance between our x's get closer and closer to 0 of that difference quotient. So when you take the limit, that's the definition of an instantaneous rate of change, or a rate of change at one point. So remember, the average rate of change, we call that a secant line between 2 points. If we're doing an instantaneous rate of change, then we call that a tangent line. Now, for those of you that have had trigonometry before, don't get the secant and tangent here confused with the trigonometric secant function and a tangent function. We're just looking at lines. Theoretically, let's scroll in here. If we're wanting a tangent line at P, we're looking for the slope of the line that pretty much just touches P along that curve. Okay, it just kind of butts up, snuggles up right next to that curve at P. That's the line that we want a slope of. So as Q gets closer and closer and closer, in other words, that distance H gets smaller and smaller and smaller, then theoretically we're approaching that tangent line. Slope of a tangent line equals your instantaneous rate of change, which is also our derivative. So don't freak out. You're not going to have to find the limit of that slope every single time. There are shortcuts. We're going to show them to you later, but we need you to understand theoretically what you are finding when you're finding the derivative. All right, so let's focus on the instantaneous rate of change. We want to find the instantaneous rate of change for the following functions at the given x values. So that means, remember, when we're looking for the instantaneous rate of change, we have to find the limit as h approaches 0 of our difference quotient. So that's f of x plus h minus f of x all over h. So when we are finding these, we have to find f of x plus h. So let's do it in pieces instead of trying to write it all at once. So we want to know what the function will look like if instead of just an x, we have an x plus h. So that means everywhere there's an x in that function, we're going to plug in x plus h. So we have to expand the x plus h squared. So if you need to FOIL it out to the side, go ahead and do that. But that will give us an x squared plus 2xh plus h squared. And now we're going to distribute the -2, -2x minus 2h. And now we can put all of that into our difference quotient. And we can simplify that. Even before we write down the limit, we want to figure out just what this piece is going to look like up here. So we're going to do f of x plus h minus f of x all over h. So this part right here is our f of x plus h. So let's put that guy in first. We have x squared plus 2xh plus h squared minus 2x minus 2h, so that's the first guy, minus, and now we want the original function, the f of x, so that's what we have up here. The original was an x squared minus a 2x. All of that is over h. And so when we write that together, see, we have an x squared plus a 2xh plus an h squared minus a 2x minus 2h, so nothing at the beginning changes. But remember, we have to subtract the entire second function there. So we have to distribute that negative. That's where most people make their errors, okay? So you might want to put in a big, caution, distribute. So that will give us a minus x squared plus 2x all over h. Now, if we have done this correctly, every term in the top that does not contain an h should reduce. We have a positive x squared, we have a negative x squared, and then we have a negative 2x and a positive 2x. every remaining term should have an h in it. That leaves us with a 2xh plus h squared minus a 2h all over h. And now that means that h can reduce with every h above. So we can think of it this way. We can factor out an h up top. We factor it out. We'll have a 2x plus an h minus 2 all over h. These h's reduce. Yay! That means we can find the limit fairly easily because it's just a nice polynomial expression. So step 3, let's actually find the limit as h approaches 0 of 2x plus h minus 2. That means we can just plug in 0 for the h because it is defined there, and we get the function 2x minus 2. That is the limit. Okay, it is the function of the limit. It's 2x plus 2. We want it at x equals negative 2. Okay, so that would be kind of our step 4. So at x equals negative 2, that's going to give us a 2 times negative 2 minus 2, which gives us a negative 6. So the instantaneous rate of change of that function at negative 2 means if we were to draw that tangent line where x equals negative 2, it would have a slope of a negative 6. So let's do the same thing for b. So let's figure out what just the f of x plus h is. So that would give us 2 square root of x plus h. Now let's go ahead and write the difference quotient. So notice that even after we write it out, unlike before, we don't have all the terms to reduce yet. And so there's nothing reducing with that h. So here's a little manipulation that is often used when we've got square roots. But usually when we try to get rid of the square root of the denominator, we would use what we call the conjugate. But we're going to do it now to get rid of the square roots in the top. So we're going to take this guy and we're going to multiply the top by 2 square root of x plus h plus 2 square root of x. But if we multiply the top, we also have to multiply the bottom. So notice this looks exactly like our numerator, except it has the opposite operation there in the bottom. Instead of minus, it's a plus. So the reason we do this, remember conjugates, you square the first, you square the last, but the outside and inside term add up to 0. So if we were to multiply these two together, we would get 4. And the square root squared just gives us what's on the inside, x plus h. And then notice these outside would get us a positive 4, square root of x plus h, square root of x. The inside would give us a negative 4, square root of x plus h, square root of x. So those add up to 0. And then we multiply these last two, and that gives us a negative 4x. And in the denominator, I'm going to leave that h on the outside, and I'll show you why here in a minute. Square root of x plus h plus 2 square root of x. So now notice what happens on top. If we distribute the 4, we get a 4x plus 4h, but we still have that minus 4x. So our h's are still going to reduce. We get 4h over h. 2 square root of x plus h plus 2 square root of x. Our h's reduce. And now we get a function that we can take the limit as h approaches 0. So even though we still have an h in the denominator, it's not just an h. So we can plug in 0 for that h and still be okay. We'll still be safe. So I wanted to show you an example like this one, not necessarily that you're going to come across one like it, but when we have square roots, sometimes it doesn't come out as nicely as our other polynomials. So let's take the limit as h approaches 0 of this function over 2 square root of x plus h plus 2 square root of x. That means we can just plug in 0 for our h plus 0 plus 2 square root of x. So that gives us 4 over 4 square root of x, because they both have the square root of x, and that reduces to 1 over the square root of x. No more h's. But remember, we still have to do it at x equals 4 up there. So last thing we're going to do, take the value at x equals 4. So we get 1 over the square root of 4, which gives us an instantaneous rate of change of 1/2. So one thing that students often have trouble with is, when do we use which? You need to know just by reading the problem whether they're looking for a secant, an average rate of change, or an instantaneous rate of change, or maybe not a rate of change at all. Maybe they just want you to plug in a value. So don't get hung up on which section are we in, I'll need to do this or that. Think of it like an exam where all the problems are mixed in together. What will be your clues as to your approach? We need to pay close attention to what it is we want to find. That also includes the number of points involved and the units. Okay, so our first example, we have a company's profit function for producing and selling Q number of modems is represented by the function P of Q equals 1000Q minus 2Q squared, where we can only make between 0 and 300 modems, and P is the profit in dollars. So first of all, it asks how much profit will the company make if they sell 150 modems. Well, notice they're just asking how much profit. P is our profit, and they're giving us Q, the number of modems. So we just plug it in. There is no rate of change here, no limit, no slope. So we want to find P of 150. So we get 1000 times 150 minus 2 times 150 squared. And if I put in my calculator right, that gives us $105,000. So again, what does that mean? That means if we sell 150 modems, we will make $105,000 in profit. Yes, it's nothing about a rate of change. Now in part B, it's asking us, will the profit increase or decrease? Increase and decrease is kind of a hint that we're looking for some sort of slope, right? Increase or decrease and going up or down. Now they're going from two different Q values. They're going from 150 modems to 250 modems, but then they're asking how fast. Okay, so that's like a velocity. How quickly are we going to be doing this? So in other words, how much money per modem will we be gaining or losing? So this is a hint that we're looking for a secant, slope of a secant function, or finding the average rate of change. So let's first find the y values that we need for this function. So we're going to find P of 150, which we already found above to be $105,000. So there's 1 point, 150 and 105,000. We need to find P of 250. That gives us 125,000. So that gives us the point of 250, comma, 125,000. And now we can find the slope. So the average rate of change, which is the slope of the secant line, could be 125,000 minus 105,000 over your 250 minus 150, which gives us 200. Okay, and remember, it's dollars on top and modems on the bottom. So that's $200 per modem. And since it is positive, we have a positive slope, that means it's increasing. Our profit is increasing by $200 per modem. So we could say, when going from 150 to 250 modems sold, that's like our time frame, right? Our profit, which is what we are studying, increases by approximately $200 per modem. Now, the last one is saying at what rate is the profit increasing or decreasing? So again, that's a rate of change, but they're asking for only a single production level of 200. We know what it's like kind of going from 150 to 250, and it might fluctuate in between there, but it's an average of $200 per modem. But we want to know at that single production level, you know, is it going up or is it going down, and by how much? So this means we need to find the limit, which also means we need to find P of, and we can use Q plus H. So we're going to plug in the Q plus H. That gives us 1,000 Q plus 1,000 H. We have to square the Q plus H first and then distribute the -2. So we get a -2Q squared minus 4QH minus 2H squared. And then we're going to write our difference quotient. Don't forget to distribute the negative there at the end. That becomes -1,000, and that becomes a positive 2Q squared. So we can take the limit. Now let's go ahead and reduce that. So our 1,000 Q's reduce, -2Q squared and 2Q squared reduce, leaving us with 1,000 H minus 4QH minus 2H squared over H. So all of those H's are going to reduce. So now we're going to take the limit as H approaches 0. H is in the first term reduced, leaving us with 1,000. H is in the second term reduced, leaving us with a -4Q. And one of the H's in the last term is going to reduce, leaving us with a -2H. And if we take the limit as H goes to 0, that gets rid of our last term, and we're left with 1,000 minus 4Q. But now we want it at a production level of 200. So at Q equals 200, we're going to get 1,000 minus 4 times 200, which also gives us 200. So we also have an instantaneous rate at $200 per modem. So we would just say at a production level of 200, our profit is increasing by $200 per modem. All right, that is it for 1.6. Good luck, everybody. Bye.